In the last lecture of electric vehicle, we have started with some examples. Okay, we know what is the amount of force that will be required to accelerate one particular vehicle. Okay, so we have gone through different equations. Like if you want to know the torque developed by vehicle, okay, I am talking about the vehicle torque, then it is nothing but the force multiplied by radius of the wheel. Okay, similarly, if you wish to calculate the power required, then it is nothing but the force multiplied with velocity of the vehicle. Okay, so we know this particular thing. Then we were talking about the dynamics of vehicle. Okay, so whenever you want to accelerate a typical vehicle from its rest period, then you need to generate the tractive force. Okay, and that tractive force has to overcome certain resistances. Okay, so we have gone through the aerodynamic resistance, rolling resistance, uphill resistance. Okay, so these three resistance are to be overcome, and then our tractive force, generated tractive force, will allow the vehicle to move in a particular direction. Right? So we have created some tractive force by the powertrain. Okay, so that tractive force will first overcome these resistances, and then it will provide the accelerations. Okay, so talking about the total tractive force, okay, that total tractive force or traction force, it is given by, the first is acceleration force, plus it has to overcome aerodynamic drag, plus rolling resistance, plus gradient resistance, which is also known as climbing force. Okay, so that was the equation of the traction force. Now talking about the acceleration force, acceleration force is generally given by m into a, where m is my gross vehicle weight and a is the acceleration. Okay, and it is in dv by dt. Then we have aerodynamic drag. So aerodynamic drag is given by half into rho into cd into a into v square, right, where rho represents, does anyone can answer, it is coefficient, right, cd is drag coefficient, and a is the upfront area, frontal area of the vehicle, and v is nothing but the velocity of the vehicle. So we have seen in case of aerodynamic drag, it is the function of the square of the velocity. So if we increase the velocity, now my aerodynamic drag is going to increase, and that is what we have seen in yesterday's example also. Okay, we have considered the case of a two-wheeler whose torque was calculated, whose aerodynamic drag was calculated by us. Okay, so at 30 km per hour, we have calculated the aerodynamic drag, which was equal to 22.5 Newton, and for same vehicle, when we have calculated the drag at 80 km per hour, it was around 160 Newton. Okay. Then we have these two resistances, rolling resistances and gradient resistance. Okay. So this rolling resistance is given by mg mu cos theta. Okay. But as we know, the value of theta is generally limited to 12 degree to 13 degree, and whenever we consider that much amount of degree, the cos theta becomes nearly 1. and this is the reason why we can neglect the cos theta. Okay, so ultimately we are left with this equation mg into mu. And if we talk about the climbing force, then climbing force is given by mg sin theta. Okay, and definitely m is the gross vehicle weight and g is the gravitational force. Okay, so this was the traction force given by the electric vehicle, right, or any vehicle. Petrol vehicle will also generate the same tractive force. After that, let us talk about the energy. What will be the energy consumed by vehicle whenever it is in motion? Okay, so whenever our vehicle is in motion, at that time the energy consumed by the vehicle is nothing but it is the integration of traction power, right? And we know how we are going to calculate the traction power, right? The traction power is given by traction power, let us say P track, is nothing but the traction force multiplied with velocity of the vehicle, right? So this is the amount of traction power, and whenever you integrate this traction power with respect to time, we will be able to get the energy consumed by the vehicle. Okay, so the energy is given by integration of traction power times dt, and unit will be watt into second. Okay, so this energy is represented by watt into seconds, but generally we represent energy in kilowatt hour, right? So this is the reason why this energy needs to be converted to kilowatt hour by dividing this equation by 3.6. So this is the energy, actual energy consumed by the vehicle. Now this energy consumed by the vehicle will define the efficiency of the vehicle. And as we have discussed that whenever we talk about the petrol engine vehicle, its efficiency is around 18 to 22% in terms of four-wheeler we are talking about. And if we consider the electric vehicle, then we are generating the traction power using electrical motor, and electrical motors will have very high efficiency. Okay, you will find electrical motors having efficiency ranging from 60% to 90%. Okay, in case of induction we are having 90% of the efficiency, so efficiency wise it is very much higher, right? So that particular electric vehicle will now consume less energy if we talk about, okay, and that energy is being consumed by the battery in our case. Okay, so each and every vehicle whenever it is running, we know that whenever we apply braking we may have regenerations. Okay, so this vehicle which has regeneration will convert the deceleration of vehicle while going down or otherwise applying braking into regenerative energy. So what will happen now? We are consuming certain amount of energy, and whenever the vehicle will regenerate, we will use that energy also, right? So if we talk about the net energy consumed, then it will be less, somewhat less. Okay, so if we talk about the net energy consumed, net energy consumed is given by R into energy consumed by the vehicle. Okay, where this R is called regeneration efficiency. Okay, now what do you mean by this regeneration efficiency? Suppose we talk about the regeneration efficiency equal to 100%. Okay, then what will happen? The net energy consumed ideally would be equal to 0. Okay. Suppose we talk about regeneration efficiency is equal to 50%, then the net energy consumed will be 50% of the total energy consumed by the vehicle. That is integration. Whenever we do the integration of traction power with respect to time, it needs to be multiplied by 1 by 2. Okay, so you can say only half of the energy will be consumed. But for an electric vehicle, as of now, the regeneration factor, if we talk about the regeneration factor, its value is typically 15% to 30%. Okay, so value of R is nothing but 1 minus regeneration factor, and it is equal to 0.85 to 0.70. Okay, so this is the typical value. Whenever we apply braking, that kinetic energy is to be converted into electrical energy, and it is fed back to the source, which is battery in our case, and we will use this energy to charge the battery again, or we will supply that particular energy to different auxiliaries of the electric vehicle, right? So that we are using this regenerated energy, and this is the reason why the actual energy consumed will be less than the energy consumed by the battery, right? But this regenerating efficiency is only 50 to 20%, right, as of now, and lot of research is going on to improvise this particular regeneration efficiency. Okay, so if you are able to regenerate the to increase the regeneration efficiency to 70% to 80%, then the actual amount of energy consumed by the battery will be very much less, and we will be available with a highly efficient electrical vehicle, right? So we will have to consider this regeneration factor also while calculating the actual energy required by the vehicle, right? Now let us talk about the power again. Okay, so what will be the power which is required to move the vehicle on the flat road, or if I have to climb some road, then what will be the power required to climb this particular road? Okay, so climbing power, whenever it is required, it is nothing but a function of velocity only. Okay, as I have told you. Okay, this is my traction power, which is a function of velocity. Okay, so this equation can now be used to calculate the power required to climb also. Okay. So let us talk about the power required to climb. Okay. So the climbing power required is nothing but a function of velocity, right? So say Pg will be equal to Fg into V. Okay, this is the equation, right? And generally when we talk about the climbing, this climbing is carried out at lower speed always. Okay, you also have tried, you also ride the vehicle, and whenever you are climbing up a grade, at that time you may observe that we are using the lowest speed. Okay, so this is the general tendency that climbing is carried out at lower speed. Okay, so this is the basics of the climbing. Okay, now let us try to understand the power, actual power required for acceleration in this particular case. Okay, so you must know the force required to reach certain speed. Okay, so actual question is what will be the force required to reach the maximum speed, say Vf, in time t seconds. Okay, so suppose we have this particular case. Whenever we talk about to climb certain distance, say this is my final speed to be achieved, and this is the time in which I want to reach that maximum speed. Say maximum speed is Vf and time required is t. Okay, so in this particular time I will accelerate my vehicle and I will reach to this point. Okay, so to reach this maximum speed Vf in time t second, what will be the force required? Okay, now here I have assumed the linear acceleration. You can see, okay, a straight line, a linear line is there. Okay, so we have assumed linear acceleration, but this is not the only option. Okay, so the actual force required to reach the maximum speed in time t seconds, it depends on how acceleration is taking place. Okay, and this is one of the option. We have assumed here the constant linear acceleration. Right? So our question will be, what is the force required to reach maximum speed, maximum speed Vf in t seconds. Okay, so as I have discussed, it depends on how acceleration take place. Okay, so we have assumed our first kind, that is linear acceleration. Okay, so assuming constant linear acceleration. Okay, so now how acceleration is provided? Acceleration A is nothing but, what will be there? It will be equal to final speed divided by time t. Okay, so final speed is meter per second, time is second. So this is the acceleration in our case whenever we have this linear constant acceleration. So A can be defined by Vf by t. Okay, now A is known to us. Okay, so we will be able to calculate the force required, right? So force required will be equal to m into A kg into meter per second square. Okay, so this is the amount of force required to reach the final velocity Vf in time t second. Okay, and during this time, what is the distance that has been traveled by this vehicle? Okay, so the acceleration distance is given by half at square, right? Acceleration distance, let us say s, is given by half a t square. Okay, so this is the amount of distance covered by the vehicle, and during this, what will be the amount of work done during this duration? Okay, so the work done during acceleration is given by acceleration force into distance traveled. Okay, so that is equal to m into a into half at square. Okay, so it will be equal to half vm vf square, a square t square will be replaced by this vf square according to equation of acceleration af is equal to vf by 2. Okay, so this is the work done. Okay, now if we talk about the power, okay, then we need to calculate this power in two forms. First is what is the amount of power required by the vehicle to move from this position to final position in certain time t. Okay, so it will take some average power, right? So we need to consider the average acceleration power also, as well as the maximum power also, which is called as peak power. Okay, so the average power, acceleration power, is nothing but the work done divided by the total time, right? So average acceleration power is nothing but the work per time. So it will be equal to half into m into vf square by t. And then what is the peak power required? The peak power required is given by m into vf square by t. Okay. This is the maximum amount of power which is required for a vehicle to reach the final speed vf, or you can say maximum speed vf in time t second. Okay. So this is one case whenever we have assumed the constant linear acceleration. Okay, so we will be able to calculate the maximum power as well as average power required for this particular case. Now let us understand another case. Okay, so what I am doing, see, to reach the maximum speed vf in time t seconds, now initially I will accelerate more and then slowly I will decrease my acceleration. Okay, and let us say what happens to the power requirement in this case. Okay, so I am considering this case. See, I am accelerating more initially like this, right? Okay, let me go here for say first half t by 2 seconds, right? So this is my t by 2 seconds. So first half time I will accelerate with more value and then I will decrease my acceleration, say almost half value. Okay, so this is say acceleration a, and this is acceleration a1, and this is acceleration a1 by 2, and this is my acceleration a. Okay, so you can see in first half time I will accelerating my vehicle with the value of a1, and during next half cycle I am accelerating with half of the value of a1. Okay, and let us see what happens. Okay, so here for first t by 2 seconds I am accelerating my vehicle. Okay, if a vehicle accelerates at a rate say a1 for first t by 2 time, and at a rate a1 by 2 from t by 2 to t. Okay, so this is our second case. Now what will happen? My final value will be Vf minus V0 will be equal to A1 into T by 2 plus A1 by 2 into T by 2. Okay, so we will be available with 3 by 4 A1 into T. Okay, so A1 is given by Vf minus V0 into 4 by 3 T. Okay, so this is our case. Now you can see the acceleration is Vf minus V0 into 4 by 3t. That means whenever you will calculate the power, so power required at this time t will be 4 by 3 by 4, that is 0.667 of that for linear acceleration case. Okay. So we have consumed the requirement of power, right? The power required at time t is 0.667 of that for linear acceleration case. Okay. So now let us calculate the average power required for acceleration. Okay. So we will consider the same case of two-wheeler which we have considered yesterday. Right. And let us try to understand this. Okay. So we are about to calculate average power required for acceleration. Okay. So our requirement is to reach maximum speed in, let us say, 20 seconds. Okay, so we are considering the case of two-wheeler. Okay, and the maximum speed is 25 kilometer per hour, or if we convert it into meter per second, then we will get 6.95 meter per second. Okay, so we have a vehicle which needs to be reached at 25 kilometer per hour speed in first 20 seconds. Okay, so let us say our acceleration is given by Vf by T, right? So force required will be equal to, acceleration force required will be equal to m into Vf by T. Okay, vehicle weight is 190, Vf is 6.95 meter per seconds, and time required is 20 seconds. Okay, so the force required will be 66 Newton. Okay, and from the force, let us calculate the torque required. The torque required is equal to force 66 into vehicle radius, which was 0.28. Okay, so torque required is 18.5 Newton meter. Okay, so this is what we get. Now we have considered the constant linear acceleration. So we have these equations. Average power is 0.5 into m into Vf square by T. Okay, so let us calculate the average power required. The average power required is equal to half m Vf square by T. Okay, that is 0.5. Weight is 190. Vf is 6.95 whole square divided by 20 seconds, and that is around 229 watt. Okay, this is the average power required. Now let us calculate the peak power required. Okay, peak power will be double that of average power, right? So it should be equal to m into Vf square by T, that is 190 into 6.95 whole square divided by 20, which is around 458 watt. Okay, so for a two-wheeler to reach 25 km per hour in 20 seconds, the average power required by the vehicle is 229 watt and the maximum power required is 458 watt. Okay. So now this is the torque 18.5 Newton meter which is required. Okay, so it is easily available. This much amount of torque will be generated by the motor, but you can reduce the torque demand in case of faster acceleration, because whenever acceleration value is increased, what will happen? The torque demanded will be higher than this 18.5 Newton meter and the motor will not be able to generate that much amount of torque every time, right? So what we are doing, we are using the gear ratios. Okay, so torque can be reduced by faster acceleration in beginning and it's slower later on. Okay, now let us consider second speed, say 50 km per hour. Okay, so now I have to reach 50 km per hour in 20 seconds. Okay, that means I have doubled my maximum speed. Okay, so force required now will be equal to 119 into 50 km per hour. When converted into meter per second, it will be equal to 13.89 divided by 2. So force required will now be equal to 131.94 Newton, and that for generation of that much amount of force, the torque required is given by 131.9 into wheel radius, that is 0.28, so it will be equal to 36.94 Newton meter. Okay, so this is my case, and average power required for this case is obviously half m into Vf square by T. Okay, so upon calculation you will get 916.43 watt. Okay, so this is my average power required, and we know the peak power requirement will be double of that. Okay, so peak power required is equal to 1832.85 watt, that is 1.83 kilowatt. Okay, now see the change. The power required to reach 25 km per hour in 20 seconds is 229 volt, and it increases to 916 volt whenever you want to reach 50 km per hour in 20 seconds. Okay, so this is the difference. Now this one is for two-wheeler. Okay, we have considered the case of two-wheeler where the torque to be generated by motor is 18.5 Newton meter and 36.94 Newton meter. It is easily available. Any motor can generate this much amount of torque, okay, without requiring any gear ratios. Okay, but when we consider the car or other vehicles, heavy vehicles, then what will happen? Okay, so let us consider the scenario of car where maximum speed is 50 km per hour or 13.9 meter per second. Radius of wheel is 0.31 meter given to you. Okay, and you have to reach this speed in 20 seconds. So the force required is m into Vf by T. Let us consider weight 1200 kg, 13.9 divided by 20. Okay, so 833 Newton force will be required. Okay, That means the torque required by the motor is equal to 833 into wheel radius 0.31. What is the torque requirement now? You can see 258 Newton. In previous case it was maximum 18.5 and 36.9, 37 Newton meter, and that increases to 258 Newton meter. Okay. So this particular application will require proper gear ratio. Okay, it will require proper gear ratio to bring it down as motor